See this tiny Hot Wheels logo? Did you know there's a science to making it look exactly the same, no matter what size it is? Today on Hot Wheels Labs, we're talking about scale. Hey guys.
Hey.
See how this big sign is like my t-shirt and this Hot Wheels car?
Yeah?
One shape, three sizes. It's what we call a scale model.
A scale model?
Let's go to the lab, I'll show you. Check it out. It's the Bone Shaker, a Hot Wheels original. Yeah, a classic. It's a pretty big deal, but this is bigger.
Wow!
The full-size Bone Shaker. So it's pretty similar, right? What's the difference?
The size!
That's right. A scale model is a copy of a real object that's made at a bigger or smaller size. How many of these do you think it would take to make up the length of this?
143. 100.
All right, let's test it out. That's the scientific way to find out if you're right. That's about 64 Hot Wheels sized Bone Shakers to make up the length of the big Bone Shaker. Now let's see how many match the width of the front. 64. That's the length and the width. Now there's one more measurement.
Height.
That's right, 64. It takes roughly 64 toy Bone Shakers in every direction. So we say this toy is made at 1/64 scale. Or you can say that it's made at 1:64 ratio, which means 1 inch on the small car is like 64 on the big car. That way the shape remains the same.
Cool.
I know. Scale models come in all different sizes. There's 148, 112, this one's 1/7.
Can a scale model be bigger than the original thing?
Of course, just like the Hot Wheels sign was bigger than the small logo. Oh, anything can have a scale model at any size. I gotta go. Don't forget to watch more videos. Ah! Energy, power, can be stored in many different ways. Batteries, fuel, even rubber bands. Stretch it and whoa! Today on Hot Wheels Labs, elastic energy! Woo-hoo-hoo! Hey guys, want to see Hot Wheels do a loop without pushing it? A booster or a gravity drop?
Yeah, right.
How are you gonna do that?
We have another source of force. We're going to use the power of elasticity. The energy you use to stretch or distort a rubber band is stored as potential energy until you release it.
That seemed expensive.
It was.
And how does that make a car go?
Experiment time. Come on. We're going to use a car that runs on rubber bands. This is the speed winder. The rubber band goes in here, and we twist it just like this. The more we twist, the more stored energy, the faster it goes. Let's try it on the loop.
All right.
We've been using these small speed winders with small rubber bands, but we also have the big speed winders with more rubber bands, which means
More elastic energy.
Faster Hot Wheels.
that's right. Let's wind them up. Let's wind them all up. Here's how it works. Matter is made up of tiny molecules, and elastic things are made of long chains of molecules. When a force distorts, these long molecules, they just want to return to their original shape. The distortion can be a stretch, or it can twist around itself. The potential energy still gets saved. When the energy is packed in, but not yet released, it's called tension. When you finally release the force, the long molecule chains rush to jump back to their original shape and release all the energy. What else is elastic?
Oh, bungee cords.
Oh, trampoline.
Yeah, and some metals.
Metals aren't elastic.
But they can be. A spring has an elastic shape, making even metal an elastic.
So cool.
Yeah, come on, release the energy! Be sure to watch more videos! Woohoo! Ever wonder how a Hot Wheels car races on walls or a loop without falling? What holds it up? Today on Hot Wheels Labs, G-forces!
Huh. The car stays on when it's moving, Why is it staying on now?
It won't stay on because it's missing something.
Tape?
It's missing G-force.
Like an astronaut.
Yes! Astronauts experience G-force and test pilots. But so do Hot Wheels. And so do you. Experiment time. Grab those Hot Wheels cars. Let's put them here. Yeah. Now, if we drop these cars from the same height with the same speed, they'll hit the bottom with the same force each time. And let's load in the cars. Launch them. But if the force is the same and the loop size is different, let's see what happens. Let's assemble these together, guys. All right. Let's try this again. Drop them in. The smaller the loop, or radius of the curve, the more we change the direction of the force, so the more G-forces we generate. In order to make the loop, the car needs more force than the force of gravity, or more than 1 G. The G in G-force stands for Earth's gravity.
More than the force of gravity?
Yeah. If you change the acceleration or change the direction of motion, you feel G-forces. But like when you're in a car and it speeds up and turns.
Oh, it's like a heavy feeling when you get pushed back in the car seat.
Exactly. You know, some race car drivers speed up so fast that they feel 5 Gs. That's like weighing 5 times more than normal. You want to beat gravity?
Yeah, let's do
Let's
this.
get some G-forces going on here. The banking walls are like loops inside them. Be sure to watch more videos! Woohoo! Hot. Perfect for melting this solid block of ice with my favorite Hot Wheels car frozen inside. Huh? Don't ask. The sun will add energy to this to turn this ice into water and then into steam. Solid, liquid, gas. Today on Hot Wheels Labs, the 3 states of matter.
Nothing! Ooh, I think I saw a drip.
This may take a little longer than I thought. That's a lot of solid to transform into a liquid. How does it do it? Let's head into the lab and find out. You guys start stacking those Hot Wheels cars for me.
Yes, sir. Yes.
Pack them tight. Stack them on top of each other. Nice. Almost everything in the world exists in one of 3 forms.
Solid, liquid, and gas.
Or air. But they can change into another form.
Like ice melting into water.
Yes. The molecules, the tiny particles that make up matter, can be organized in a different way. Let's start with a solid, a stack of cars. Now, when the molecules, or in this case, the cars, are packed in tight, it's heavy, organized. You can pack a lot into a small space, but not much room to move around. A solid. But if you add energy, go ahead and put your cars in here. Then the molecules will need to move around. Let's add some energy. When the molecules move more, they lose their organization and shape. That's why a liquid will take the shape of whatever container it's in. And if you add even more energy, the molecules move farther apart and become a gas. Because there's so much space between molecules, a gas fits into any container you put it in. Hot Wheels, cool car. Today, a Hot Wheels Labs mini episode. States of matter, liquid to solid. Adding or subtracting energy is only one way of changing the state of matter. Pressure and chemistry can also do it. I can show you with the Hot Wheels Fusion Factory. It changes a liquid into a solid using a chemical reaction. This contains 2 chemicals. When I insert it and the car mold into the Fusion Factory, I can pump it into the car mold like this. When I do that, the 2 chemicals mix, the molecules latching onto each other in a chemical bond that turns liquid into solid. Now, we wait for the chemicals to combine. Time's up. Now, we see what we've got. Take it out of Fusion Factory. And we have a solid. Pretty cool. Power on. This battery-powered Hot Wheels booster is gonna help our cars get enough power to get through those super big loops. All right! Today on Hot Wheels Labs, Power Ups. How batteries work. Awkward.
Put the car in the booster. What?
Hey, what's up with that booster?
I just turned off.
Probably got some dead batteries in here. Did you guys know that electricity is stored inside batteries?
Really?
No.
Yeah, but it doesn't last forever.
Why not?
Let's build some track and I'll show you why.
Okay.
All right, guys, check this out. A battery is like a garage, except instead of holding cars, it holds electricity. Each one of these cars inside there represents an electron. If you can get all of those electrons flowing in the same direction, then you can create an electric current.
Like a river?
Exactly like a river. Now, let's start sending these electrons down the ramp. If you can get enough electrons flowing in the same direction, then they can do work for us. They get things moving. And harnessing that power is how the modern world works. So what happened?
It's empty.
Time to recharge. All right, let's see what this booster can do. Add that to the track and get some loops. Let's do this. Now that's power! Keep watching Hot Wheels Labs! Woo! Ever wondered how people went from getting around like this to getting around like this? A big part of it was figuring out how to use the energy stored in fuel. Today on Hot Wheels Labs, the science of combustion!
Yeah!
All right. Nice loops, guys.
Heard your truck outside. Pretty cool.
Oh, yeah, it is. You guys have a nice setup in here. So how did your cars get enough power to go through these loops?
Boosters.
My truck doesn't have to drive through a booster to go fast, right? It just has an engine. You guys know how an engine works?
No.
Combustion. Let me explain it to you. Here's what a simple engine looks like inside a car or a truck. You've got air and gasoline that enter the chamber here. In an internal combustion engine, the expansion of the high temperature and high pressure gases produced by combustion applied direct force to some component of the engine. That's what breaks down the gasoline and explodes. That's called combustion. All the heat gases inside here, plus the gas pushes down against the piston, and eventually makes all the tires go. You know?
Not really.
Let me try this a different way. A mix of air and fuel enters the engine. It's squashed by the piston, compression. Then an electric spark makes it blow up, pushing the piston to help these wheels move. Let's try it with Hot Wheels.
Whoa!
Yeah, I told you it was cool. All right, guys, here it is. Our Hot Wheels combustion engine. These white cars, they represent oxygen. These yellow cars, they represent the gasoline. We have to send them both into the engine at the same time. They're gonna fire into the engine, and they're gonna hit the spark plug. And that's gonna give us our boom, right? That's our combustion. These red cars represent that heated gas that's created from that explosion. That heated gas builds up and has nowhere to go, but it has to get out of that engine. So it has to fight its way through the pistons. These are our pistons right here. What happens after that?
The wheels move. Tires move.
That's exactly right. It makes those wheels move. Who wants to give it a try?
Me!
All right, get in there. Send this oxygen and gas into the engine. Oh, nice! Did you see that? The wheel's moving. The thing is, there's not just one piston in the car. There's several pistons. They all work together. So, who wants to see this thing in high gear? Let's set it up. Let's get going. Ready? 1, 2, 3. Sound of a combustion engine! Cool sound. But why does a car sound different coming than when it's going? Find out on today's Hot Wheels Labs. Sounds fast. The sound of Hot Wheels speeding down a track. Did you guys know the sound is another kind of energy? It's called vibrations. And those vibrations are affected by speed. You wanna try it out?
Yeah!
All right, I got just the thing. Let's go get it. So, I put this buzzer on top of this car. I also put a tiny microphone on it. And there's a microphone here near the end of the track. Both of those mics are connected to this oscilloscope. This device shows us sound waves so we can see them. Let's see what we can hear. Give it a try.
Ready? Go.
All right, let's see what the microphone on the track gave us.
Awesome.
Yeah, that's the Doppler effect. You think we'll hear the same from the mic on top of the car?
Probably.
Let's see. Does that sound different?
Yeah.
Yeah, why?
I have no idea.
Let me tell you why. Sound is made of waves of energy. If you're traveling with the sound, it doesn't seem to change at all. But waves coming toward you sound different from waves going away. In the direction you're going, they get smushed. Behind you, they get drawn out. It's called the Doppler effect.
Are there really waves in sound? Yeah, I can't see them.
Well, the sounds we normally hear travel through air, and we can't see that. But sound travels through everything, through liquids and even solids. Let me show you. Let's see how sound travels through this liquid. See, the high tones make small waves, and the low tones make big ones.
Whoa! Did you see that? Awesome!
Check this out. All kinds of sounds. But we all know the best sound is race cars.
Yeah!
Woohoo! There's nothing like speed. Actually, there is. More speed. Today on Hot Wheels Labs, gravity!
How fast? 1 second.
Whew, what a rush. What are you two up to?
We're seeing how fast this car could go down the ramp. We did it in 1 second.
Well, let me ask, how far do you think you could go in 2 seconds?
I guess twice as far.
Let's find out.
Yeah!
All right, so 1 second, it reached this first yellow line. How far do you think it's gonna go in 2 seconds?
To here?
Okay, that's a really good guess. All right, count me down. 3, 2, 1.
Go!
Oh, wow. It made it all the way here in 2 seconds. That's 4 times the distance that it made it in only 1 second, because gravity is acting on it all the way down the ramp. Now, for this third test, let's get the flags out. Are you guys ready to see how far it goes in 3 seconds?
Oh, yeah!
All right, 3, 2, 1, go! In 3 seconds, it went 9 times the distance that it went in 1 second. You know what that is? Acceleration. Means it speeds up. And do you know what causes acceleration?
Gravity.
That's right, gravity. And Sir Isaac Newton told us that everything wants to be pulled to the biggest, closest object nearby. And for everything here on Earth, the closest, biggest object is the Earth itself. That's right. So it doesn't just work for Hot Wheels cars, though. It works for everything. You guys want to try it out?
Yeah!
There we go.
There's nothing like gravity!
You guys are probably thinking, that guy's on a track with no car. He's going nowhere. But guess what? When that gate releases, I'm out of here. Buckle up for today's Hot Wheels Labs.
Invisible energy!
So close.
Trying to make the jump, huh?
Yeah.
You need more potential energy.
My mom says I have potential.
My mom says I have a lot of energy.
I'm talking about something different. Come on up here, let me show you what I'm talking about. All right, so tell me, does this car have energy?
Yes.
It does, kinetic energy, moving energy. What about this car? Does this have energy?
No.
It doesn't look like it does, because it's invisible. That's potential energy. It's all about where something is or how it is. And this car had potential energy because of its distance from the ground. I know exactly the experiment to show you. You wanna go check it out?
Yeah.
Yeah.
Let's go get it. All right, guys, the reason we have 6 tracks is because when you increase the height, you're also increasing the potential energy. I call it the splat test. Who wants to get started?
Yeah.
All right, let's go.
Did you just see it go through like that? It just went left bing and then go everywhere.
That was at 6 feet. What do you think would happen at 10 feet?
Oh, I just go right through it.
I want to see it at 30 feet.
Yeah!
Then let's do it.
Whoa! There's lots of potential here.
That's right. All this height gives us gravitational potential energy because the car has the potential to be pulled down the ramp by gravity. Here we go. Oh, but there are other types of potential energy too, like elastic, mechanical, in a wind-up car, nuclear.
Hurry up!
All right, let's do this.
Yeah! Biggest jump ever!
I know one even bigger, for maximum potential energy. There's nothing like going fast. But right now, looks like I could use a way to stop.
Today on Hot Wheels Labs, friction!
You can't stop the swamp of doom. Because Hot Wheels don't stop!
Science to the rescue.
Saved by Sam.
Oh yeah, we did it.
How did Sam save him?
Well, when the tires dragged against the sand, it created friction. And it sent the energy of the car into the sand.
What's friction?
Let me show you. Friction happens when different surfaces rub against each other, sharing the energy of one object with another. Different materials have different levels of friction.
Different levels.
Yeah. Let's build some track.
Yeah!
All right. Each one of these tracks has a different surface at the bottom. So first, let's check out the ice. The smooth track has less friction and more speed. The rough track has more friction, so less speed.
Less speed? Why would anyone want more friction?
Good question. Sometimes you want to put on the brakes. Brakes on a real car work by applying friction to the wheels to get it to stop. All right, we'll try it your way.
Yeah!
Friction and braking are great for real cars, but sometimes you gotta do things the Hot Wheels way.
Are we crashing Hot Wheels today?
Oh, don't worry, we're crashing plenty of Hot Wheels today. Look, let's try the first experiment. Crash this car into that one. When car 1 collided with car 2, it gave most of its energy, its momentum, to car 2.
One car pushing another car? What's the big deal?
Let's see what happens when we add more cars. Launch this second experiment.
How'd that happen? How come only the last car moved?
Let me explain. Conservation of momentum means that the motion that goes in is the same as the motion that comes out. Let me show you guys something. You can see it clearly with this Newton's cradle. So this first car hits with a certain amount of force. That force is passed from object to object as they hit until almost the same amount of force comes out the other side. Check it out.
Whoa.
Yeah. That works for Hot Wheels and real cars too. Now we know why my car moves when a car way, way back there gets hit. All thanks to Sci. That's it for today's Hot Wheels Labs!
This is one of my favorite Hot Wheels cars. Which do you think will hit the ground first, me or the car? Today on Hot Wheels Labs, we're talking about wind resistance!
So, what hit the ground first?
The car!
Why would a tiny car fall faster than a much larger scientist?
Because you had a parachute.
Yes, it's because of resistance. Wind resistance.
What's wind resistance?
Well, when I jumped out of that airplane, gravity pulled me and the car down, but the air was pushing back up against us. You see, air is actually made of tiny molecules. They're just too small for us to see, but they can slow us down. This is called resistance. And because I had a big parachute, there was more surface area for the air to push against, so there was more air resistance to slow me down. In fact, anything that travels through another substance encounters resistance. To demonstrate, we're gonna need to build a Hot Wheels track.
Yes.
So, we know air has resistance. What about water?
Whoa, it really slowed down.
Yeah, that's because water has even more resistance than air. Because it has a higher density of molecules. Or more stuff is in the way. What else has resistance? Notice how the Hot Wheels car slows down differently each time.
So different materials have different resistance?
Precisely. On Earth, you can't escape resistance. In fact, the only place you won't find resistance is where there's no air, like outer space. Don't forget to watch more Hot Wheels Labs!
Ever wonder why a race car looks so cool and sleek? Find out today on Hot Wheels Labs, built for speed.
3, 2, 1.
Race, yeah.
Man, this is my favorite car.
But how come his is faster?
Let's see. Yeah, these cars weigh the same, so it must be something else. Their design. Their aerodynamics. The science of how air affects moving objects, like cars. To demonstrate, let's put those cars in a wind tunnel so that we can see the action of the air over the shape of the cars. Air can push a car, and when that car wants to speed forward, it has to fight against the air. Let me explain this a little better. Air is made of tiny particles. The bigger a thing is, the more air particles it has to push. Check out the shapes of these vehicles. The van's face is flat, hitting air particles head on. But the race car's shape is pointed and curved so it can slice through air, forcing air up and over it. It's time to mix it up a little bit. Here are your cars.
This doesn't look like it's gonna go faster anymore.
It's because I added a little something extra to it so that it almost matches the shape of the van. So, time for a rematch. When it comes to real cars, aerodynamics is super important. The special shape of race cars reduces the impact against the air in front of them. And one more cool thing, the force of the air above now pushes down on it, pushing the tires against the road for better grip. And that means
More speed!
more speed! Hey, what's up, kids? Oh, looks like I am. Because today on Hot Wheels Labs, we're talking about the science of loops. Ouch.
Why didn't the car make the loop? Yeah, how the Hot Wheels loops worked anyway?
Well, the car didn't make the loop because it wasn't going fast enough. It didn't have enough energy to overcome the force of gravity. When a Hot Wheels car is speeding down a track, it has driving force. But gravity is always applying a downward force too. If the driving force isn't greater than the force of gravity, it can't go through the loop. Let's try a little Hot Wheels experiment. Give this car a little bit of push with just a nudge of your finger. All right. Now, give a little more force to that one with a good push.
Hey, this car went farther than that one did.
And that's because we gave it more force, but it still wasn't enough to overcome gravity. So it's time to crank this science into high gear. Give this car even more force.
This is gonna be good.
These boosters give this car some extra force.
Let's test it out.
This time the force of the car was greater than the gravity pulling it down, so it was able to go through the loops without falling. With enough force, this car could go through even bigger loops.
How big?
Pretty big.
I love science!
If this truck suddenly rockets into action, what will be your reaction? Today on Hot Wheels Labs,
Action-packed! Spectacular! New record!
You were so fast out there. Yeah, that jet action was awesome.
an action that led to a reaction. Let me explain, but I need your help. Let's build some track, and we need some balloons.
Yeah. So cool.
This experiment uses the third law of motion. For every action, there is an equal and opposite reaction. So the action of the energy rushing from the back of the jet engine creates the reaction of air outside of the jet engine pushing back. That's not all. The third law of motion happens for every action. In this case, when a real car moves forward, its tires push backwards on the road, and the road responds by pushing the car forward. Looks like you got the experiment set up. Let her rip.
Awesome.
Air pushes backwards and forwards. Tires push down, the track pushes back. The car pushes into another car, and the second car pushes back. You guys ready for some more crashing?
Yeah.
The third law of motion applies to every action everywhere. action always leads to reaction.
And my reaction is... that this is action!